Hello everybody, I am Syed on Maths Online. Today's topic is derivation of one-dimensional heat equation. To derive this equation, some basic and empirical laws are required. The first law is heat flows from a higher temperature to a lower temperature. We can get an idea of this law from the second law of thermodynamics. That means heat always flows from a higher temperature to a lower temperature. The second law is the amount of heat in a body is proportional to its mass and temperature. Whenever you take the amount of heat is always proportional to the mass m, and it's always proportional to the temperature T. This law also you have studied. And coming to the third law, the rate of heat flow across an area is proportional to the area and to the temperature gradient normal to the area, where the constant of proportionality K is called the thermal conductivity. Here the thermal conductivity K is defined as the ability of a substance to conduct the heat. Now we'll try to study in detail about this third law with the help of this figure. So we'll consider a rectangular slab. So let me draw the rectangular slab. Let us consider this rectangular slab, and let us consider the initial point of the slab to be equals to O. Let this cross section of the slab be equals to P, Q, R and S. The second cross section be P dash, Q dash, R dash and S dash. Now you are supplying this heat from here. Heat is being supplied from here. So heat flows along this rectangular slab and reaches this cross section of the slab. Let the distance from the initial point to the point P be equals to, say, x. This is the distance. Again the heat moves from the slab and reaches this second cross section, and the heat comes out of this rectangular slab. Let this distance be equals to delta x. From the first cross section to the second cross section, I am taking the distance to be equals to delta x. So as the heat moves along this rectangular slab, and this rectangular slab is similar to this rectangular slab that we have over here. So you can see the rectangular slab over here. So this is a rectangular slab similar. So heat is being transferred from one end from here, right? And I am taking the first cross section over here, somewhere over here, which will represent here PQ, R and S. So as the heat moves forward, there is another cross section I am considering over here. So I am trying to study in between these how much of heat flows, right? So if that is the case, so this third result, the rate of heat flow across an area is proportional to the area and to the temperature gradient. So the rate of heat flow, so when the heat is flowing, how much of heat flows through this? It depends upon this area, more the area, more the heat flows, less the area, less the heat flows. So here also, based on the cross section, the heat will flow through this cross section. And also the heat of rate flow depends upon the temperature gradient, the change in the temperature, normal to the area. So the heat which is flowing, this is the cross section, is PQRS. The heat is flowing from here exactly perpendicular. So heat flows perpendicular to the rectangular slab. So the rate of heat flow also depends upon the temperature gradient normal to the area. And as I told you, K is the thermal conductivity. Now let us consider this bar, and this bar is a homogeneous bar. It's a uniform rectangular bar that I am taking. So we'll consider, you can simultaneously take down the notes. That's the reason why I'm writing down in the form of statements. So consider a homogeneous rectangular bar. Homogeneous rectangular bar. I am taking the cross-sectional area of I'm taking the cross-sectional area to be A, and let us take the density of this rectangular slab to be equals to rho. Rho is the density of the rectangular slab, and because the heat is flowing through this rectangular slab, the specific heat, alright, the specific heat can be taken to be equals to S, small s, alright, and the thermal conductivity. So we have the thermal conductivity. Let us take that to be equals to K, right? And we can see that as the heat flows through this rectangular slab, it flows along, say suppose if I am taking this as the x-axis, the heat flows along the x-axis starting from the origin, right? Suppose if I take the temperature of this rectangular slab to be equals to U. The temperature of the rectangular slab is taken as U. So heat flows through starting from the origin and reaches this cross-sectional area. So the cross-sectional area over here is PQ, R and S. So consider the element of the bar. Consider the element of the bar between the planes. So what are the planes that we are taking? We are taking the plane PQ, R and S, and the plane P dash, Q dash, R dash and S dash. This is what we are taking, P, Q, R and S, and P dash, Q dash, R dash and S dash. These are the two planes that we are considering, and this PQRS plane is at a distance, it is at a distance of x from the origin. That is what I have taken, distance x from the origin, distance of x, the first case, and this P dash, Q dash, R dash, S dash is at a distance of x plus delta x from the origin, O. The temperature changes at every point. So the change in temperature between this slab to this, between this rectangular region to this rectangular region, suppose if I take the change in temperature to be equals to change in temperature, we are taking it as delta U. Now this change in temperature delta U takes place in this region only, in this region of delta X. So this change in temperature is taken place in a slab thickness in a slab thickness of delta x. Now let us try to see what will be the mass of the element. The mass of the element. Mass of the element will be, means only this element we are considering. What will be the mass of this element where the heat enters and the heat leaves the cross section area? So as we know, the basic definition of mass will be nothing but it is density into volume. That's the basic formula that you have. So mass m, density over here is rho into what is the volume that we are having. Volume over here represents your area into the length. So what is the area that we are taking? Area we are taking it as A. What is the length? What is the length that we are considering? This one, delta x. So therefore it is rho A into delta x. Rho A into delta x, that represents the mass of the element. Now what will be the quantity of heat stored? The quantity of heat stored in the slab element. In the slab element will be equals to, what will be the quantity of heat stored? The basic formula that you have for the quantity of heat stored, if I am taking it as Q, the basic formula that we have is, it is mass into the specific heat into the change in temperature. The change in temperature. This is the basic formula for the quantity of heat stored. So we want to know what is the quantity of heat stored in this region. That is what we are trying to calculate. So that is the basic formula you have. This. So now what is the mass? Mass is already known. So mass over here is nothing but rho into A into delta x. That is the mass. What is the specific heat? The specific heat we already taken. It's nothing but S into, we have the specific heat as S into the change in temperature. So what is the change in temperature that I have taken? The change in temperature I have taken as delta U into, you get delta U. So that is the quantity of heat stored in the rectangular slab. So now if I try to rewrite this expression, so let me rewrite this as it is A rho, the specific heat, S delta x into delta U. So this represents the quantity of heat stored in the rectangular slab. So as you know that as the heat flows, there will always be a change. The heat flowing inside will be different from the heat flowing outside this region. So what will be the rate of increase of heat in this rectangular slab? The rate of increase of heat in the slab element. So if suppose if I am taking the rate of increase to be R, so R will be equals to the quantity of heat stored that we already know. The quantity of heat stored is, it is A rho S delta x. A rho x delta x. That is the mass into specific heat, and it depends upon the change in temperature. The rate of increase in the slab depends upon the change in temperature dou U by dou T, and the mass, that is A rho delta x into the specific heat. So rate of increase depends upon this mass, specific heat, and the change in temperature. Now further, if you want to write down the rate of inflow, how much of quantity of heat is flowing through the first rectangular first cross section area. So if I take that as the rate of inflow, Ri will be equals to the rate of inflow, where I represents over here, I represents the inflow. I represents the inflow. So rate of inflow is given by the Fourier's law of heat conduction, which is nothing but it is minus K into A times of dou U by dou X. And this rate of inflow is at a distance of X from the origin. So the change in that temperature is at a distance of X. So first rectangular slab that I am taking. So here what will be the rate of inflow? This will represent your Ri, rate of inflow. Then similarly, what will be the rate of outflow? Ro, let me consider. Again it will be minus Ka into, it is dou U by dou X, and it is at what distance? Rate of outflow, this, what is the rate of outflow? That is at the cross section P dash, Q dash, R dash and S dash. Therefore it is at what distance? The total distance is, this is X and this is delta X. The total distance is X plus delta X. So it is X plus delta X. So this negative sign which we have taken over here, the rate of inflow as well as rate of outflow, and because this dou U by dou X which we have, this dou U by dou X, which is a rate of a change of temperature with respect to the distance. So as heat transfers from one end to the other end, the change in temperature will always decrease. So as the heat enters over here, the heat is more. As the heat moves away, comes out, the heat will be less over here. Because the change in temperature will always be decreasing, therefore this dou U by dou X will be negative. But the value of R should be positive over here. Therefore we have taken this as a negative sign. That negative multiplied by this negative will become positive, and the value of R will be equals to positive. So that's the reason we are taking the value of R to be negative. So what will be the rate of increase in the temperature? R will be nothing but the rate of inflow minus the rate of outflow. That will be the rate of increase in the heat. So how much of heat is being increased when the heat enters from here? So rate of increase in the temperature. So we are taking Ri at this point. We are taking Ri at this point and Ro at this point. So rate Ri, because the heat entering is more, so first we are taking that one, and rate of outflow R0, which is less. So a greater value minus the smaller value will give you the positive value. So we know the value of R. So the value of R is known from here. So this is the value of R. So let us write down this value of R. So suppose if we take the value of R there, it is A rho S delta X times of, it is dou U by dou T is equals to, Ri value is known from here, it is minus Ka into dou U by dou X minus Ro. So this particular value, it is minus Ka into dou U by dou X, that is X plus delta X, which will be equals to, it is minus Ka into dou U by dou X at X. So this minus of minus will become plus, Ka into dou U by dou X, X plus delta X. Or if I write first positive value then the negative value, and you can also take the value of Ka common outside. So I am taking Ka common outside. So first positive value I will write, it is dou U by dou X, X plus delta X. Then here it is a negative sign, it is minus dou U by dou X at X. Because I need to find out this value of dou U by dou T, so let's take all these values that we have over here on the other side. So if you want to rewrite this one, it will be dou U by dou T will be equals to this Ka divided by what you have, it is A rho S delta X times of, it is dou U by dou X x plus delta x minus dou u by dou x at x. We know this a and a will cancel out. We'll be left out with k by, it is rho times of s. So let us take delta x on this side. It becomes dou u by dou x at x plus delta x minus dou u by dou x at x whole divided by, I am taking this delta x over here, times of delta x. So as I take that limit delta x tends to 0, so it gives us the value as k by rho times of s. So this represents your partial derivative. It becomes dou by, because delta x tends to 0, it is dou by dou x of, what is the value you have? Dou u by dou x. Dou u by dou x, which will be nothing but, it is k by rho times of s. This is nothing but dou square u by dou x square. So this gives you dou u by dou t is equals to, suppose this k, rho and s all are constant, and can replace that by some other constant, c square dou square u by dou x square. So this is dou u by dou t. Now this gives us the heat equation. Or if you want to rewrite this one, you can write ut, because dou u by dou t represents ut value is equals to, it is c square times of, again this can be written in the form of u, because it's second order derivative with respect to x, you can write u xx. This also represents the heat equation. So you can write down the heat equation either in this form or in this form. So this represents the one-dimensional heat equation. So I've given you the complete notes from the beginning. You can just go back, try to see the video from the beginning and make the notes. That's all I have for today. Thank you.